Hello dear students, welcome to Pen and Paper Chemistry on YouTube. We are finally on to part 13 of our set of videos on amines, and today we shall be covering the topic of electrophilic substitution reactions. And I sincerely hope that you have your pen and notebook from the earlier lessons ready so that we can learn and write together. So let's get started. A quick overview on electrophilic substitution reactions. We know that our benzene ring is electron rich because of the presence of the pi electron cloud. So it attracts species which are looking for electrons, and these species which are looking for electrons are known as electrophiles. Now these electrophiles, they come and replace one of the hydrogen atoms and take the place on the benzene ring, giving us an electrophilic substitution reaction. An electrophile replacing one of the hydrogen on the benzene ring. Understand the difference in the two. So this is replacement of an electrophile on the benzene ring. We have done so far in general 5 electrophilic substitution reactions we have spoken about in most of the organic chemistry topics that we have done, and those are nitration, sulfonation, halogenation. Can you recall what are the other two? Go ahead, think about what we've done in the previous lessons. Yes, we've already covered phenols and haloarenes, have we? Yes, that is the Friedel-Crafts reaction. Friedel-Crafts, there is alkylation and there is acylation. Yes, you could recall. And what are the catalysts used during each one of these, which is the electrophile in each of these reactions? We have already covered all these details under the heading the basics of organic chemistry, and we have covered them under mechanisms. Now is the time to understand the electrophilic substitution reactions in the case of amines. Do amines show all of these reactions that we have mentioned? Now as you can see over here, amines, because they are electron rich at the nitrogen atom, they are electron donors, and because they will release electrons towards the benzene ring, it is the ortho and the para sites which become electron rich, and our amino group is ortho para directing. Also, because it is releasing electrons towards the benzene ring, it will be ring activating. It gives electrons to the benzene ring. Okay, now go ahead and draw the canonical structures of aniline. Be mindful of the charges which will be there on each of the atoms. Yes, it is very easy to wait for me to write it and you will copy it. But why don't you gain confidence by drawing the canonical structures yourself, and in return sending me a smile in the comment section? Oh, I'm not a drawing teacher at all. I just like to see big smiles. Okay, so go ahead, draw the canonical structures. Now if you notice over here, I have written a statement that anilines do not show Friedel-Crafts alkylation or acylation. Now why does that take place? First of all, let's relate our learning to our previous slides, wherein we have already spoken about reactions where aniline reacts with, acyl halides and haloalkanes and benzoyl chloride and anhydride. So if you haven't watched those videos, time to do that now. So our aniline will also react with acetyl chloride. But you see over here, We are carrying out Friedel-Crafts reaction in the presence of anhydrous AlCl3. So what is the problem? If the reaction is being carried out in the presence of anhydrous AlCl3, the reaction should take place normally. But also remember that our aniline acts as a Lewis base and AlCl3 is a Lewis acid. Perfect combination for a good friendship. So what happens over here is the Lewis base and the Lewis acid combine to form a product. Yes, you have the ion over here, C6H5NH2 positive. They are going to form yes, obviously a salt, an acid and a base combining to give us a salt with the result. Or did you draw the canonical structures? Yes, this is how you have to go about it. So negative charge comes here, double bond. Do not forget the positive charge on the nitrogen. Yes, that's the formal positive charge. And don't forget the double-headed arrows. And here the electron cloud moves. Do you still remember them from our earlier learning? Yes, we've already covered resonance on the channel. Don't forget the double-headed arrows for canonical structures. Again, the electron cloud moves. Why am I coming back to the canonical structures again? You will see that in a little while. So double bond NH2, let's expedite this, and we have this double bond remains unaffected. It is in its place, and then we have, see, the electron has come back to the nitrogen. So NH2, and we have the lone pair of electrons, double bond, double bond, double bond. Now, the AlCl3 takes advantage of this and it engages this lone pair of electrons with itself. Now, when it has engaged the lone pair of electrons towards itself, no, it is not exactly like this. We have to show the electron sharing, but try and understand. So, because our electrons are now engaged with AlCl3, do you think that these canonical structures will be possible? Will our benzene ring get electrons at the ortho and the para centers? No way. So, do you think electrophilic substitution reaction will take place in the presence of, in the case of aniline? So, when we are talking about acylation, alkylation in the presence of anhydrous AlCl3, no, it's not taking place. And the same thing we have written over here. Aniline forms a salt with anhydrous AlCl3. This reduces the electron donating capacity of the nitrogen. So what is happening now is, now it is actually hungry for electrons and it has become ring deactivating. It deactivates the ring towards substitution. So that is why no Friedel-Crafts alkylation or acylation reactions take place. See? Out of 5 reactions, electrophilic substitution reactions that we spoke about, 2 are, you strike away 2 of them. Is that so? Wait. What about nitration, sulfonation, halogenation? Let's quickly have a look at bromination, which you do as a test also in the laboratory in order to identify aniline. So here aniline on reacting with bromine water at a room temperature gives you a white precipitate. Do you recall doing this test in the laboratory? Yes, of course. So aniline on reacting with bromine water gives us a tri-substituted product. It's an electrophilic substitution reaction, and we know that aniline is highly ring activating. So it doesn't wait for the mono-substituted product, it directly goes on to, so we don't stop the reaction at the mono-substitution state, and we get the tribromo, how should I name it? Can you help me out with this? Go ahead. 2, 4, 6. What will be the primary functional group? Go ahead and recall the IUPAC system of nomenclature. So these reactions, this reaction goes on to show that our NH2 group is highly activating. What if I want a monobromo product? What do? We prevent the activating effect of the NH2 group by using the fundamental that we had spoken about over here, where the NH2 group can act as a nucleophile. The nitrogen, because of its electron rich center, it can behave as a nucleophile and engage with the C double bond O group carbonyl. So NH2, instead of engaging with the benzene ring, it gets busy with the carbonyl group, and we are able to reduce the activating effect of the NH2 group. Let us understand how. Aniline, you reacted with the acetic anhydride, but not in the presence of anhydrous AlCl3 as we had done in the case of Friedel-Crafts acylation reaction. We are using a base over here, a stronger base. With the result, our NH2 group gets busy with the acetic anhydride. Yes, you recall this reaction, substitution on the NH2 group. N-phenyl ethanamide, or also known as acetanilide. I am sure you will be able to recall it as C6H5NHCOCH3. That's our acetanilide, and we have spoken about these in our earlier slides. Now, the lone pair of electrons on the nitrogen is actually busy with the carbonyl. So we will have the possibility that there is lower possibility. We are not saying that there is no possibility, but there is the number of canonical structures where the nitrogen goes on to the electrons of the nitrogen go onto the benzene ring becomes less, because our electrons are now engaged with C double bond O group as well. So you will have additional canonical structures. Have you completed these? Tell me, there's something missing in my canonical structure. Can you point it out? Yes, the positive charge on the nitrogen. Please don't forget that, because our aniline is still neutral. Now you see over here, there we had drawn the canonical structures of aniline, and we had this state. Now there are additional two canonical structures which will come into the picture if C double bond O CH3 is also there. C double bond O CH3. Now here our electrons will get engaged with the carbonyl group as well. Now our electrons are not as readily available to the benzene ring. If they are available, yes, they will be available on the ortho and the para positions, but our ring does not become as electron rich as when this C double bond O CH3 is not there. So that makes our understanding easy. Now, if I carry out the bromination using bromine and acetic acid, easily I will get two products, the ortho and the para. But look at the ortho. I have not written the ortho product, because if we form the ortho product, look at the crowd that is going to develop next to each other on two adjacent carbon atoms. So in this case, the major product over here, remember, it's the major substitute. It's not that the ortho product is not going to form, but our major product will be the para substituted aniline. So how are we going to name it as? Para bromo aniline, right? And how are we going to do that? First step is, of course, para bromo acetanilide. After we carry out the hydrolysis in an acidic or basic medium, we get para-bromoaniline. We don't jump straight away from N-phenyl ethanamide to para-bromoaniline. Look at the steps. First is halogenation. on the acetanilide, and then we want our NH2 group. Don't forget, don't lose focus, because our focus was to bring about halogenation in the aniline. So what are the steps of this conversion? And this entire step or this entire process is called protecting the NH2 group. That means protecting it or preventing it from releasing too many electrons onto the benzene ring. So look at the steps. First, aniline reacted with acetic anhydride in the presence of a base. We get acetanilide. Carry out its substitution with any agent. So supposing you want to carry out bromination, chlorination, you get the mono-substituted product where the para-substituted is in the major amount, followed by hydrolysis to re-release the NH2 group and get the mono-substituted product. Please go ahead, write this reaction down. I will keep it on the screen so that you can note down for reference later on. Next, electrophilic substitution, nitration. Now we know that NH2 group is highly ring activating. So if we try to nitrate it directly using nitric acid, now nitric acid also is a very strong oxidizing agent. So what will happen is it is going to give us a lot of tarry products, a lot of side products because of the oxidation that will take place. If I carry out nitration using nitric acid, concentrated HNO3 and concentrated H2SO4 at 288 Kelvin, interestingly again, because of the ring activating effect of the NH2 group, I'll get the ortho-para products. But at the same time, you see, we are carrying out the reaction in the presence of nitric acid. Our aniline is a good, it's a good base, and our nitric acid is a good acid. So what will we get? We will get a salt over here. So base combining with an acid, we get the anilinium. Yes. Let's again connect our learning to ammonia. Ammonia plus H positive gives us NH4 positive. So this was ammonium. Similarly, when you have aniline C6H5NH2 plus H positive, you get C6H5NH3 positive, and this is from aniline, I'll get anilinium. Now, our electron pair on the nitrogen is no longer available to the ring, and this becomes ring deactivating. Well, now my ring is deactivated, means where will the substitution take place? Meta substitution. So can you write the products which will be formed here? Yes. So with regard to aniline, you will have nitro group at the ortho position. With regard to the NH2 group, you will have nitro at the meta position. With regard to NH2 group, you will have nitro group at the para position. So we have a mixture of ortho, meta and para substituted products. Ortho, meta, para, nitro, aniline. What's the way out? Yes, exactly. Protecting the amino group and then getting only the para substituted product. What are we going to do again? We'll take aniline. We will protect it using acetic anhydride in the presence of pyridine. It will give us acetanilide. And then you carry out nitration with HNO3. You will get the mono-substituted product, carry out the hydrolysis, and you will have just the para-nitroaniline. What do you have to do for me? You have to complete this reaction for me. Please complete. And let me know in the comment section if you could confidently go through it or not. Please complete this reaction here. Sulfonation. Again, if I talk about sulfonation, recall that aniline is a base and H2SO4 is an acid. So again they are going to combine together to give you the anilinium ion. Remember we just now did, so it's going to form C6H5NH3 positive, HSO4 negative, anilinium hydrogen sulfate. If we heat this in the presence of H2SO4 at 453 to 473 Kelvin, interestingly it does give us what we call as para-aminobenzene sulfonic acid. Oh, don't worry, let's write the reaction, it will become easier to understand. So our aniline with concentrated H2SO4, aniline hydrogen sulfate. So as you see, our nitrogen was electron rich, so the study could have been so simpler, but it has complicated the matters for us. Now when you heat it, you get over here what we call as sulfonilic acid. Here this is a product which has a basic group and an acidic group at the same time. So there can be mutual transfer or mutual sharing of this hydrogen between so the H can be here or the H can be here. If H goes over here, my nitrogen is going to acquire a positive charge and an SO3 will acquire a negative charge. Now when this happens, I have a product where I have positive and negative charge within the same molecule. We are not talking about an ion over here, this is within the same molecule. In other words, here there is a resonance between these two structures, and this is what we call as a Zwitter ion. You are also going to study this under the topic of proteins. Is that so? Amino acids. Yes, absolutely right. You've already done it under the topic of biomolecules. No, we have not covered that topic on the channel. So this forms a Zwitter ion when reacting with sulfuric acid. So on sulfonation, we actually get aniline hydrogen sulfate, which on further treatment only is giving us the para-substituted product. Now I'm going to leave you with some work over here for me to do. Please compile the uses of aniline or aromatic amines and make sure that your notes are completed and all in one place so that you can revise them for the exams. Missed out anything, I'm going to post these notes and these slides on the Google site Pen and Paper Chemistry. So what you have to do is just Google Pen and Paper Chemistry and it will lead you to this logo. That's the YouTube channel and the Google site, and on the Google site you will find many helpful charts, flow charts, and on the YouTube you will find corresponding lectures on or lessons on how to use these charts. So these are just examples of, like, carboxylic acid. I've given one part of it, and there's phenol. There are much more material on the Google site, and more is sure to follow. In fact, these slides also I will post it onto the Google site very soon. Thank you for your patience. Thank you so much for taking time to comment and making my day a really happy one and infusing me with energy to continue with this project. All the very best and a very happy learning to you. See you in the next video very soon.